One of these cities is sinking so fast the government is building a new capital on a different island. Then there's a country where the pumps have never stopped running. Not once in 800 years. Because if they do, the sea takes back a third of the nation within days. So today I'm counting down 10 places on Earth that are actively, measurably, irreversibly sinking. Number 10, Jakarta, the city being left behind. 17 million people live on ground that is disappearing beneath them. Not slowly, not gradually in the way that geological change usually works. In North Jakarta, the land has dropped 2 meters in the last 10 years alone. 2 meters, roughly the height of a standard door frame, gone from under a living city within a single decade. The reason is groundwater. Jakarta sits on a coastal plain underlaid by massive aquifers, and for most of the city's modern history, those aquifers have been the primary water source. Pump the water out and the clay and sediment layers above compress. Not temporarily, permanently. The material that filled the space is gone. The ground above it has nowhere to go but down, and Jakarta pumped. For decades, across millions of wells, both legal and illegal, the city extracted water faster than rainfall could replace it. The aquifer didn't just drop, it collapsed inward. The physical evidence is everywhere and visible. Seawalls that were built to keep the Java Sea out of North Jakarta now stand below the waterline on the seaward side. The sea didn't rise over them. The land sank beneath them. Entire coastal neighborhoods flood not during storms but during high tide. Routine, predictable, permanent inundation that happens on a calendar. Residents in some districts have built their ground floors into de facto second floors, stacking life higher as the street outside slowly submerges. 30% of Jakarta now sits below sea level. That figure is not static. The Indonesian government's response to this is extraordinary in what it implies. They are not building a better seawall. They are not engineering a drainage solution. They are building an entirely new capital city, Nusantara, on the island of Borneo, roughly 1,200 kilometers away. The relocation has been underway since 2023. Jakarta will retain economic and cultural functions, but the seat of government is moving because the current seat of government is going underwater. That decision, made at the level of a national government costing an estimated $32 billion, is the clearest possible statement about what the engineering assessments concluded. Jakarta is not a city with a sinking problem that can be solved. It is a city whose foundation is compromised in a way that cannot be reversed. The groundwater that was extracted is not coming back. The clay layers that compressed will not re-expand. The subsidence that has already occurred is permanent, and the subsidence that hasn't occurred yet is, by most projections, inevitable. Some mitigation is happening. The government has restricted groundwater extraction in certain zones and invested in piped water infrastructure to reduce dependence on wells. In areas where pumping has slowed, the rate of sinking has slowed. Not stopped, slowed. The buildings didn't move. The earth beneath them did. And in the districts closest to the bay, where the tide now arrives uninvited and the seawalls look out at open water from below, the damage is already done. 9. New Orleans and the bowl that keeps getting deeper. August 29, 2005. The levees broke, the city flooded, and the images went around the world. But here's what those images didn't show. New Orleans was already well below sea level before a single drop of floodwater arrived. Katrina didn't create the vulnerability. It just made visible what the ground had been doing for decades. The city sits in a bowl, not metaphorically, literally a topographic depression ringed by the Mississippi River on one side and Lake Pontchartrain on the other, with the Gulf of Mexico a short distance beyond that. In the lowest districts, the land sits nearly 8 feet below sea level. That's roughly the height of a standard room ceiling, underground, in a city of nearly 400,000 people. The sinking started when the city did. European settlers began draining the swampy land around the original high ground settlement in the early 18th century, and every acre of drained swamp began to compact. Organic peat soil, when you drain it, doesn't just dry out, it oxidizes, shrinks, and disappears. The land that was reclaimed from the marsh began returning to something lower than marsh. It began returning to nothing, and then the Mississippi was levied. This is the part that accelerated everything. The river that built the delta for thousands of years, depositing sediment with every flood, rebuilding the land from below, was cut off from the floodplain. The sediment that used to replenish the surface stopped arriving. The land kept compressing. Nothing replaced what was lost. The Army Corps of Engineers pumps water out of New Orleans continuously. There are over 20 pumping stations operating at all times, moving rainfall and groundwater out of the bowl before it accumulates. The largest of these stations, the Sewerage and Water Board system on Palmetto Street, is among the most powerful urban drainage systems in the world. It runs every hour of every day. If it stops, the city floods. Not from the river, not from the lake, but from rain that has nowhere to go. And the pumping itself contributes to the sinking. Removing groundwater from below the city reduces the pressure that partially supports the surface. The ground settles further. The bowl gets deeper. The pumps have to work harder. It's a loop with no exit. Parts of the lower 9th Ward, which saw some of the worst flooding in 2005, have subsided by more than 3 feet since the 1950s. A period during which the levees were rebuilt twice and the pumping infrastructure was expanded significantly. The rebuilding didn't stop the sinking. It kept pace with it, barely. Geodetic surveys conducted after Katrina and again in the 2010s confirmed that the city is measurably lower now than it was when the post-storm levee system was completed. The ground the new levees were built to protect has continued to drop beneath them. Sea level rise compounds this. The Gulf of Mexico is rising at a rate that, combined with local subsidence, means the effective sea level relative to New Orleans is increasing faster than almost anywhere else on the American coastline. The city isn't just sinking toward the water is rising to meet it. What exists now is a city of 400,000 people living inside an engineered system, levees, pumps, floodgates, drainage canals, that requires continuous operation to maintain the basic condition of not being underwater. The system works when it works. 2005 demonstrated what happens when it doesn't. The ground beneath New Orleans has been sinking since the city chose to exist where it does. That decision was made 300 years ago, and the consequences have been accumulating ever since. At number 8, Tehran. Satellites caught it first. In the mid-2000s, radar interferometry data, the kind that measures ground deformation from orbit with millimeter-level precision, began showing something unusual across a broad front to the west and southwest of Iran's capital. The ground was moving, downward. In some zones, the surface was dropping by 25 centimeters in a single year. That's roughly the length of a standard ruler gone from under a city of nearly 10 million people in 12 months. Tehran sits in a semi-arid basin at the foot of the Alborz mountain range. The mountains feed a series of aquifers beneath the city, underground water-bearing rock and sediment layers that accumulated over thousands of years of snowmelt and rainfall percolating slowly downward. For most of Tehran's modern history, those aquifers were the answer to the city's water problem. Drill down, pump up. It worked for a while. The clay layers are what make this irreversible. When an aquifer is drained, the water pressure that was holding the clay and silt layers open, essentially keeping them inflated, disappears. The clay compresses, not elastically, not in a way that bounces back when water returns. Permanently. The pore spaces collapse, the material consolidates, and the ground above descends. Inject water back into the aquifer afterward and you recover the water pressure, but the clay doesn't re-expand. The compression is done. This is called hydrocompaction, and Tehran is one of the clearest examples of it happening at urban scale anywhere on Earth. The physical consequences are not abstract. Roads across the affected zones have developed longitudinal cracks running parallel to the direction of subsidence. Not potholes, not surface wear, but structural fractures in the asphalt caused by differential sinking across short distances. Underground infrastructure is worse. Water mains, sewage pipes, and gas lines that were laid level have been sheared by the ground moving at different rates in different places. A pipe that crosses a subsidence boundary doesn't bend, it breaks. Buildings tilt. Not dramatically, not in the way that makes headlines, but measurably. Foundations on one side of a structure sinking faster than the other, producing gradual lean that accumulates over years. In the worst affected districts southwest of the city center, some structures show visible inclination. Engineers have documented it. The buildings didn't shift. The ground beneath one side of them dropped further than the other. The subsidence isn't uniform across the city, which makes it harder to address. The highest rates, up to 25 centimeters per year in peak zones, are concentrated in areas with the densest well extraction history. Other parts of Tehran are sinking more slowly, or not measurably at all. This variation means the damage accumulates at boundaries. Where fast-sinking ground meets stable ground, the stress concentrates, and that's where infrastructure fails first. Iran has attempted to reduce groundwater extraction in and around Tehran, and in some areas the rate of subsidence has slowed in response. But slowing is not stopping, and stopping is not reversing. The clay that compressed during peak extraction years is not going to recover. The ground that dropped is not going to rise. Satellite monitoring has continued to track the affected zone, and the data shows the subsidence front has expanded over time, not shrinking as restrictions take effect, but spreading as extraction continues in adjacent areas. The problem has not been contained, it has been redistributed. Tehran's subsidence is invisible from street level in most of the city. You don't see it happening. You see the results: the cracked road, the leaning wall, the pipe that failed for no obvious reason. The ground announces itself through damage, not through spectacle. 25 centimeters a year in some zones for years running. The land sinks and nothing replaces it. 7. Dhaka, Bangladesh. 22 million people. That's the population of Greater Dhaka, roughly equivalent to the entire population of Australia, compressed into an area about the size of Greater London. It is one of the most densely populated urban areas on Earth, and it is built on ground that is actively compressing beneath it. The mechanism is the same one that's destroying Tehran, but the context is entirely different. Dhaka sits on the Bengal Delta, a vast alluvial plain built up over millennia by the Ganges, Brahmaputra, and Meghna river systems depositing sediment as they slow and spread before reaching the Bay of Bengal. Delta sediment is young, loose, and compressible. It was never rock. It was always going to compact under weight. The question was always how fast. The answer, it turns out, is faster than anticipated. Groundwater extraction is the primary driver. Dhaka's municipal water supply system has historically been unable to keep pace with the city's explosive growth. The population roughly doubled between 1990 and 2010, and the gap has been filled by private wells drawing from the aquifers below. Those aquifers sit within the same soft alluvial sediment that makes up the delta. Drain them, and the sediment compresses. In the densest districts of the city, subsidence rates of up to 1.4 centimeters per year have been measured. That's not a large number in isolation, but stack it. 1.4 centimeters per year over 20 years is 28 centimeters, nearly a foot of ground lost from under a city that already sits close to river level. And Dhaka's rivers are not static reference points. The Buriganga, the Turag, the Balu, the waterways that ring the city, carry flood pulses every monsoon season that already push into low-lying districts without any help from subsidence. The combination is what makes Dhaka's situation structurally different from Tehran's. Tehran is sinking in an arid basin, away from the sea, with flood risk that is serious but not existential at the national scale. Dhaka is sinking in a delta, in one of the most flood-prone countries on Earth, with the Bay of Bengal to the south and sea levels that are rising independently of anything the city does or doesn't do. Researchers studying the combined effect of local subsidence and regional sea level rise have found that the effective rate at which the water is rising relative to Dhaka's ground surface is significantly higher than either factor alone would suggest. The ground comes down. The water comes up. The distance between them closes from both directions simultaneously. The physical evidence is visible in the city's flood patterns. Districts that flooded only during severe monsoon events 20 years ago now flood regularly during moderate ones. The flood threshold, the water level at which inundation begins, has dropped because the ground has dropped. The river doesn't have to rise as high to get in. It doesn't need to. Infrastructure tells the same story. Roads in subsiding districts develop the same longitudinal cracking seen in Tehran. Differential settlement as adjacent ground moves at different rates. Buildings constructed on shallow foundations in soft soil show uneven settling. The Dhaka Water Supply and Sewerage Authority has documented ongoing challenges with pipe infrastructure in areas of known subsidence, where ground movement stresses joints and connections that were laid level. Bangladesh as a whole is acutely aware of its geographic vulnerability. A significant portion of the country sits within a few meters of sea level, and cyclone storm surges from the Bay of Bengal have historically caused catastrophic flooding across the delta. The government has invested in coastal embankments, early warning systems, and cyclone shelters. These are responses to the water from outside. The water from below, the slow compression of the ground itself, is harder to address, less visible, and in many ways more permanent. Restricting groundwater extraction in a city of 22 million people, where the alternative supply infrastructure doesn't yet exist at sufficient scale, is not a switch that gets flipped. It is a decades-long infrastructure problem layered on top of a geology problem layered on top of a climate problem. The ground beneath Dhaka has been losing the argument with gravity for decades. At 1.4 centimeters per year, in some districts, it's still losing. Houston, Texas. Number 6. Former neighborhoods are underwater. Not flooded, underwater. Permanently. In the Brownwood subdivision in Baytown, east of Houston, houses were bought out by the government and demolished in the 1980s because the land they sat on had sunk so far below sea level that keeping people there was no longer defensible. The streets still exist on old maps. The land is now marsh. Houston's subsidence story starts in the early 20th century, when the region's enormous reserves of groundwater, and later oil and gas, began to be extracted at industrial scale. The geology beneath the Houston metropolitan area is a thick sequence of alternating sand and clay layers, saturated with water that accumulated over millions of years. Pull the water out, and the clay layers compress. The same mechanism as Tehran, the same mechanism as Jakarta, but Houston got there first and went further. By some measurements, parts of the Houston area have sunk by more than 4 meters since the 1920s. 4 meters, roughly the height of a 2-story house, gone from under the ground surface over the course of a century. The areas of greatest subsidence are concentrated in the east and southeast of the metropolitan region, particularly around Baytown, Pasadena, and the communities closest to Galveston Bay. Galveston Bay is the problem. It doesn't move. The bay sits at a fixed elevation, and as the land around it sinks, the relationship between the two changes permanently. Land that was safely above the bay's flood influence in 1920 is now within it, or below it, or gone entirely. The Brownwood subdivision is the most documented example, but it's not the only one. Across the subsidence zone, the effective flood risk for properties that haven't moved has increased dramatically. Not because of storms, not because of sea level rise, but because the ground beneath them descended. Harris County, which contains most of Houston, has experienced repeated catastrophic flooding events. Tropical Storm Allison in 2001, Hurricane Harvey in 2017, and the subsidence history is part of why those events were as damaging as they were. Land that sits lower floods sooner, drains slower, and retains water longer. The subsidence didn't cause the storms. It made the storms worse. Texas responded. Beginning in the 1970s, the Harris-Galveston Subsidence District was established to regulate groundwater extraction across the region, with a mandate to reduce pumping and transition municipal supplies towards surface water from reservoirs and the Trinity River. The regulation worked measurably. In areas where groundwater extraction was curtailed, subsidence rates slowed dramatically, in some zones effectively to zero, but the land that already sank didn't come back. Slowing the rate of future subsidence is not the same as recovering what was lost. The Brownwood houses are still gone. The marsh is still there. The streets on the old map still don't exist, and the regulation wasn't uniform. In the outer areas of the metropolitan region beyond the subsidence district's jurisdiction, extraction continued longer and in some places continues now. The subsidence front didn't stop at the district boundary, it followed the water. If you're enjoying the video, drop a like and a comment. It really does help the channel out. The entries from here get larger in scale and more permanent in consequence. And the next one involves a country that has been fighting this exact problem not for a century, but for 800 years. What the Houston case demonstrates more clearly than almost any other city on this list is that subsidence is not an inevitable consequence of geology. It is a consequence of decisions about what to extract, how fast, and from where. The Harris-Galveston Subsidence District exists because enough of the damage had already been done to make the cost of regulation feel smaller than the cost of continuing. In Baytown, where the Brownwood subdivision used to be, the marsh has been there for 40 years now. Herons nest in it. The ground is not coming back. 5. Shanghai, still building upward while sinking down. There's a tower in Shanghai called the Shanghai Tower. It stands 632 meters tall, taller than any building in the United States, taller than anything in Europe, and it is built on ground that has been sinking continuously since before its foundations were poured. The engineers knew this when they designed it. They built it anyway because the entire city is in the same condition, and stopping construction was never on the table. Shanghai sits on the Yangtze River Delta, which is soft alluvial sediment all the way down. The same category of geology as Dhaka, the same fundamental problem. Young, loose, compressible material that was never going to hold indefinitely under the weight of a modern megacity. The city began its significant modern expansion in the early 20th century, and by the 1930s, measurable subsidence was already being recorded. By the time the People's Republic of China began its systematic monitoring of Shanghai's ground levels in the mid-20th century, the city had already sunk by nearly 1 meter in its most affected areas. By the 1960s, cumulative subsidence in parts of the city had reached close to 2 meters. By the end of the 20th century, nearly 3 meters in the worst zones, roughly the height of a standard room, gone from under one of the world's largest cities over the course of about 80 years. The primary cause initially was groundwater extraction. The same mechanism as every other entry on this list. Pump the water out, the clay compresses, the surface drops. But Shanghai added a second driver that most other sinking cities don't have at the same scale: the sheer weight of construction. The Pudong district, which went from farmland to one of the world's most recognizable skylines between the early 1990s and 2010, placed an extraordinary load on the soft delta sediment beneath it. Studies have found measurable additional subsidence directly attributable to the weight of new buildings pressing down on compressible ground. Not groundwater alone, not geology alone. The buildings themselves are part of the mechanism. China's response to Shanghai's subsidence has been more technically aggressive than most. Beginning in the 1960s, authorities implemented groundwater extraction controls and, in a move that is genuinely unusual, began injecting water back into the aquifers beneath the city to attempt to partially reinflate the compressed sediment layers and slow the rate of descent. The injection program worked, to a degree. Subsidence rates that had been running at over 10 centimeters per year in the 1950s dropped significantly by the 1980s and have been kept to a few millimeters per year in recent decades in some areas. But the injection doesn't reverse what already happened. It manages the rate of future loss. The 3 meters that sank are still sunk. And the subsidence isn't uniform, which creates a specific engineering problem across the city. The Shanghai Tower, the World Financial Center, and the Jinmao Tower, 3 of the tallest buildings on Earth, standing within a few hundred meters of each other in Pudong, are each founded on deep pile foundations driven down through the soft sediment to bedrock or dense load-bearing layers far below. They are, in engineering terms, pinned in place. The ground around them is not. So as the surrounding surface continues to settle at its own rate, the relationship between the tower foundations and the street level outside them shifts incrementally over time. The towers don't sink with the ground. The ground sinks around the towers. The result, over decades, is a city whose surface is in slow differential motion, some parts pinned, some parts free, the stress concentrating at the boundaries between them. Shanghai's subway system, one of the longest in the world at over 800 kilometers of track, runs through this differentially settling ground. Maintaining tunnel alignment and preventing joint failures in a subsiding, non-uniform environment is an ongoing engineering challenge that the city's transit authority manages continuously. The tunnels are monitored, adjustments are made, the ground does what it intends to do, and the engineers respond. 3 meters of cumulative subsidence since the 1920s, a skyline that keeps rising, a surface that keeps falling. Shanghai has decided these two facts can coexist, and so far the engineering has held. What's it for? Mexico City. Mexico City was built on a lake. This is not a metaphor or a simplification. The Aztec capital of Tenochtitlan was constructed on an island in the middle of Lake Texcoco, connected to the shore by causeways, surrounded by water on all sides. When Spanish colonial administrators took control in the 16th century, they made a decision that has defined the city's geology ever since. They drained the lake. It took centuries of drainage works, canals, and tunnels to accomplish. By the 20th century, Lake Texcoco was effectively gone, replaced by the expanding urban fabric of what had become one of the largest cities on Earth. But the lakebed remained, and lakebed sediment, the fine clay and silt that accumulates at the bottom of a body of water over thousands of years, is among the most compressible material a city can be built on. Mexico City is built on approximately 50 to 100 meters of this material in its central and eastern zones. Not rock, not consolidated soil. Saturated lacustrine clay that behaves under load and drainage more like a slow-motion liquid than a solid foundation. The compression began as soon as the lake was drained and the water table started dropping. It accelerated through the 20th century as groundwater extraction beneath the growing city pulled moisture from the clay layers, causing them to consolidate and shrink. The numbers are staggering. In the historic center of the city, the ground has subsided by approximately 9 to 10 meters since the colonial drainage began in earnest, roughly the height of a 3-story building, removed from beneath the surface over the course of a few centuries. In some active zones today, subsidence continues at rates of up to 25 to 30 centimeters per year. That's nearly a foot of ground lost annually in a city of over 20 million people. The Metropolitan Cathedral of Mexico City, which sits on the Zócalo, the main plaza of the historic center, is the most visible evidence of what this does to structures. Construction on the cathedral began in 1573 and continued for over 200 years, which means different sections of the building were completed at different times, on ground that was already subsiding at different rates in different places. The result is a cathedral that lists, tilts, and undulates. The floor is not flat, the walls lean at varying angles, and the whole structure has required continuous engineering intervention for decades. Since the 1993, engineers have conducted an extraordinary remediation project on the cathedral, selectively extracting soil from beneath the parts of the foundation that had subsided least, allowing those sections to sink further and bringing the structure back toward level, not lifting it, deliberately sinking the high parts to match the low parts. It's a controlled, incremental process that has measurably reduced the cathedral's tilt, and it has to be monitored and adjusted continuously because the ground beneath it is still moving. The cathedral decided it was going to lean. The engineers decided to negotiate. Across the historic center, colonial-era buildings show the same differential settling in varying degrees. Facades that no longer meet at right angles, door frames that have racked out of square, foundations that have cracked along the boundaries between faster and slower subsidence zones. The problem is not that the buildings are old. The problem is that the ground beneath them has been in continuous motion since they were built. The subway system, the metro, presents a related challenge. Lines that were built level have subsided differentially, requiring ongoing track maintenance to keep gradients within operating tolerances. Stations in the Lake Zone district sit lower than they were designed to sit, and the tunnels connecting them have bent slowly with the ground. Mexico City has invested in reducing groundwater extraction and importing surface water from outside the basin. The subsidence rate has slowed in some districts in response. But 9 to 10 meters of cumulative subsidence in the historic center is not a number that improves. The clay that compressed is compressed. The ground that dropped is dropped. The lake has been gone for centuries. The lakebed remembers exactly what it is, and it has been saying so 1 centimeter at a time ever since. 3. The Netherlands, a country that decided to exist anyway. 26% of the Netherlands sits below sea level. That's not a rounding error or a measurement of low-lying coastal strips. It's nearly a third of a sovereign nation, home to roughly 17 million people, occupying land that the North Sea has a prior and ongoing claim to. The Dutch didn't find this land, they made it, and making it required a commitment to continuous mechanical intervention that has now lasted without interruption for the better part of 800 years. The story starts with peat. The western and northern Netherlands were originally vast peat bogs, thick accumulations of partially decomposed plant matter that sat at or just above sea level, saturated with water, held in place by their own moisture content. Beginning in the medieval period, Dutch farmers began draining these bogs to make them farmable. They cut drainage ditches, lowered the water table, and put the land to agricultural use. It worked. And then the peat began to do what drained peat always does. It dried out, oxidized, and shrank. Not slightly, dramatically. Peat that loses its water content can compress to a fraction of its original volume. The land that was drained dropped, in some areas by meters, below the level it had occupied before the drainage began, below the level of the rivers, below the level of the sea. The farmers had converted bog into farmland, and in doing so had converted land that was marginal into land that was actively below water without continuous intervention. The Dutch response was the windmill, not as a romantic symbol, as a pump. Thousands of windmills were built across the low-lying polders to lift water from the drainage ditches up into the rivers and canals that carried it to the sea. When the wind blew, the pumps ran. When the wind didn't blow, the water accumulated. The system worked well enough to sustain a civilization, but it required that the pumping never stop. And then steam power arrived, and then diesel, and then electric pumps. And the capacity to move water increased enormously, which enabled the Dutch to drain even more land, which caused even more peat compression and subsidence, which required even more pumping. The cycle compounded across centuries. Today, the pumping infrastructure of the Netherlands is among the most extensive in the world. There are roughly 14,000 kilometers of dikes, thousands of pumping stations, and a network of water management authorities, the Waterschappen, that have existed in some form since the 13th century, making them among the oldest continuously functioning democratic institutions in Europe. Their sole purpose is to keep the water out of land that the water, by every law of physics, should be covering. The Beemster Polder, north of Amsterdam, was drained between 1608 and 1612 using 32 windmills working in relay. It dropped below sea level as soon as the drainage was complete. It has been below sea level ever since. It is now a UNESCO World Heritage Site, a landscape of flat, geometric farmland lying several meters below the surrounding water, held in place by dikes and pumps that have been running, in one form or another, for over 400 years. The lowest point in the Netherlands is a polder in South Holland called Noverkerk aan den IJssel, which sits approximately 6.7 meters below sea level, roughly the depth of a 2-story building underground, except it's open farmland with cows on it and a road running through it, and the only thing between it and the water is an earthen dike and a pump station. If the pumps stop, not permanently, not for a dramatic infrastructure failure, but for a few days during a storm surge, significant portions of the country flood. The Dutch know this with the precision of people who have done the calculations many times. The Delta works, a series of storm surge barriers and flood defenses constructed after the catastrophic 1953 North Sea flood that killed nearly 2,000 people, represent the most sophisticated coastal defense system ever built. The Maeslandkering barrier near Rotterdam, 2 enormous steel arms, each the length of the Eiffel Tower laid on its side, that swing shut across the waterway during surge events, is controlled by a computer system that monitors water levels continuously and makes the closure decision autonomously. The barrier has closed a handful of times since it was completed in 1997. Each closure is a demonstration of how narrow the margin is. The Netherlands is not a place that is sinking toward crisis. It is a place that resolved its crisis centuries ago by deciding the crisis was permanent. and building a civilization around managing it continuously. The pumps have never stopped, not once, in 800 years. The Mekong Delta. Number 2. 90 million people eat rice that comes from this place. The Mekong Delta in southern Vietnam is one of the most productive agricultural regions on Earth, a vast, flat, water-threaded landscape covering roughly 40,000 square kilometers, sitting just barely above sea level, feeding a nation and exporting to the world. It is also sinking faster than almost any comparable landmass on the planet, and the two facts are directly connected. The delta was built by the Mekong River over thousands of years. Sediment carried down from the Tibetan Plateau and the mountains of Southeast Asia was deposited at the river's mouth, layer by layer, building up the flat, fertile plain that exists today. That sediment is young, loose, and compressible, the same category of material as the Bengal Delta beneath Dhaka, the same fundamental vulnerability. The difference is what's happening to the sediment supply upstream. Dams. Dozens of them, built across the Mekong and its tributaries in China, Laos, and elsewhere over the past several decades, trap the sediment that used to flow downstream and replenish the delta. The river still arrives. The sediment doesn't. The delta that used to receive a continuous supply of new material to replace what compresses and erodes is now running a sediment deficit. The surface loses material faster than it gains it, and the ground descends. At the same time, groundwater extraction beneath the delta has accelerated dramatically as the population has grown and agricultural irrigation demands have increased. The aquifers beneath the delta sediment are being drawn down, and the sediment above them compresses in response. Measured subsidence rates across parts of the delta run to around 1 to 2 centimeters per year, which sounds modest until you consider that most of the delta sits less than 2 meters above sea level to begin with, 2 meters of clearance. 1 to 2 centimeters lost per year. The arithmetic is not complicated. In some coastal and estuarine zones, the effective rate of sea level rise relative to the delta surface, combining actual sea level rise with local subsidence, is among the highest measured anywhere in the world. Researchers have documented rates of relative sea level rise in parts of the delta exceeding 1 centimeter per year when both factors are combined. The land comes down, the water comes up. In a landscape measured in centimeters, that's not a slow emergency. The physical consequences are already visible and permanent. Saltwater intrusion, the infiltration of brackish and saline water from the coast into formerly freshwater channels and groundwater, has extended further inland with each passing decade. Rice paddies that were productive agricultural land 20 years ago now receive saltwater intrusion during dry season that renders them unviable for the crops they were built to grow. Farmers in affected provinces have switched to shrimp aquaculture in some areas, not by choice, but because the salinity of the water now suits shrimp better than rice. The land didn't change its use. The water changed it. Coastal erosion compounds the subsidence. Without the sediment supply that used to replenish the delta's edges, the coastline is retreating. Satellite imagery shows shoreline recession across significant stretches of the delta's coast. Not dramatic cliff collapse, but the quiet, continuous retreat of low, flat land into the sea. Mangrove forests that once buffered the coast from wave action have been reduced by decades of conversion to aquaculture ponds, removing a natural defense at the same time the coast became more vulnerable. The Cai Mau Peninsula, the southernmost point of Vietnam and the most seaward part of the delta, is experiencing some of the most acute erosion and subsidence on the coast. Villages that were inland communities a generation ago are now coastal. Some are gone. Vietnam's government has recognized the scale of the problem and has implemented restrictions on groundwater extraction in parts of the delta, alongside investment in surface water infrastructure to reduce aquifer dependence. The restrictions have had some effect in slowing subsidence rates in areas of compliance, but the sediment deficit upstream, the dams holding back the material that built this landscape, is not a problem that Vietnam can solve unilaterally. The Mekong flows through 6 countries before it reaches the delta. The decisions that affect the sediment load are made elsewhere. 90 million people depend on food produced in a landscape that is measurably, continuously, and in some respects, irreversibly losing its elevation. The delta is not going to vanish next year or in 10 years. But the trajectory, subsidence plus sea level rise plus sediment deficit plus saltwater intrusion, has no natural reversal point built into it. The river built this place over thousands of years. What's happening to it now is being measured in decades. 1. Venice, Italy, 1500 years and still asking. In the 5th century, people fleeing the collapse of the Western Roman Empire and the invasions of the Italian mainland made a decision that should not have worked. They built a city on a lagoon, not on the shore of a lagoon, in it, on wooden piles driven into the mud of a tidal flat in the northern Adriatic. They constructed what would become one of the most consequential cities in the history of Western civilization. The Republic of Venice lasted over 1,000 years. The city it built is still there, and it is still sinking. The foundation is the first thing to understand, because it's not what most people picture. Venice is not floating. It is not sitting on water. It is sitting on approximately 150,000 wooden piles, mostly alder and oak, driven down through the lagoon sediment to reach more stable layers below, which have been there, in some cases, for over 1,000 years. The wood doesn't rot because it's permanently submerged and oxygen deprived. The piles have essentially petrified in place. They hold the buildings up. What they cannot hold is the ground around them. The lagoon sediment compresses. It has been compressing since the first pile was driven in. The natural compaction of the soft mud and clay beneath Venice causes the surface to descend gradually, independent of anything the city does or doesn't do. This is called natural subsidence, and in Venice's case it has been occurring at a slow but continuous rate for 15 centuries. Then, in the 20th century, it accelerated. Between the 1910 and the 1970, industrial groundwater extraction on the mainland area of Porto Marghera, the industrial zone built adjacent to Venice across the lagoon, drew down the aquifers beneath the entire region, including beneath the lagoon itself. The sediment compressed faster. Venice sank at rates significantly higher than its natural baseline during this period, losing approximately 12 centimeters of elevation in 60 years. 12 centimeters, roughly the length of a standard pen, doesn't sound catastrophic until you understand that Venice's entire existence is calibrated to centimeters. The groundwater extraction was halted in the 1970s when the subsidence was linked to it. The accelerated sinking slowed. The natural rate resumed. The 12 centimeters did not come back. Acqua alta, high water, is the term Venetians use for the tidal flooding events that push water from the Adriatic through the lagoon inlets and into the city's streets and ground floor spaces. These events have always occurred. They are a structural feature of living in a tidal lagoon. But the frequency and severity of acqua alta events have increased measurably over the 20th and early 21st centuries for two compounding reasons. The city is lower than it was, and the Adriatic sea level is higher than it was. In 1900, acqua alta events of significant depth occurred roughly 10 times per year. By the early 2000s, that figure had risen to over 60 times per year in some years. The flooding threshold, the water level at which the Piazza San Marco, the lowest major public space in the city, begins to flood, is reached far more often than it was a century ago because the piazza is lower and the water is higher. Both things are true simultaneously. The MOSE project, Modulo Sperimentale Elettromeccanico, a system of 78 hinged metal barriers installed across the three inlets connecting the Adriatic to the Venetian lagoon, was conceived in the 1980s, approved in 2003, and completed in 2020 after decades of delays, cost overruns, and corruption investigations that resulted in criminal convictions. The final cost exceeded 6 billion euros, roughly the GDP of a small nation, spent to protect a city of approximately 250,000 residents. The barriers work. When a significant acqua alta event is forecast, the hollow metal flaps are filled with compressed air, rise from the lagoon floor, and block the tidal surge from entering. The system has operated successfully since its completion, including during events that would previously have caused severe flooding in the city center. But MOSE was designed and calibrated against current and near-term sea level projections. It has an operational lifespan. The sea level it was built to manage is not the sea level that will exist in 50 or 100 years under most credible projections. The barriers can be raised more frequently as flooding events increase. They already are. but the engineering margins built into the system are not infinite, and the maintenance costs of a structure sitting permanently on a tidal lagoon floor are substantial and ongoing. Venice has been subsiding, adapting, engineering, and persisting for 1,500 years. It has outlasted the empire whose collapse created it. It has survived plague, conquest, Napoleon, 2 world wars, and the Acqua Alta of November 1966, the worst flood in recorded history, when the water rose 194 centimeters above sea level and remained there for nearly 24 hours, damaging thousands of artworks and driving a generation of residents to the mainland permanently. The question Venice has been asking since the first pile was driven into the lagoon mud: whether a city built on water, sinking toward water, surrounded by rising water, can continue to be a living city rather than a monument to one, has not yet been answered.